In quantum mechanics, electron has a wave function that tells you where you have a maximum chances of finding an electron at a given time. But if because of that you want to say that electron is a wave, then the problem is that if position is one measurable quantity, then momentum is another measurable quantity. And there is in the same quantum mechanics, you have a momentum wave function which tells you that at a particular time which momentum has a maximum chance of being found. And the third measurable quantity is energy, and there is energy wave function which will tell you that at particular time which energy has maximum chances of being found, and then you have angular momentum wave function and so on. So that does mean that the electron as many as are measurable quantities. It seems like a puzzle, and the solution is that no, electron is one A. But what is one? And the answer to one is that there are all wave functions, no matter how many measurable quantities are there and no matter how many wave functions are there, they are all related to one. And there's a reason to say that there's one is a vector, and there's reason to say why it is a ket vector. And the reason is that actually the reason of the last thing is that ket is half of bra-ket, and bra-ket is a dot product between ket and bra, and the dot product is the transition amplitude from ket state to bra state. And a mathematical example of that dot product of bra-ket is called Dirac delta function. So that is the summary, pre-summary of the lecture, and now is the actual lecture. And where is to tell you, here I have examples of two wave functions. I said there can be as many wave functions as you have measurable quantities, and these wave function can be related as well. And the example here is that the position wave function is related to momentum wave function. If you multiply, I'm saying that because if you multiply k with h bar, that becomes momentum according to de Broglie, the boy expression. And that's nothing new. If I have shown it, I revise, and it's just pure revision that a position wave function is a combination. It's called linear combination of many plane waves. This is a plane wave, and every plane wave is characterized by wavelength, or reciprocal is wave number k, and there's a weighted factor. And the weight factor is a factor depending upon k. In mathematical terms, this means is a function of k. Weighted factor is a function of k, and k is with h bar gives you momentum. So this is the momentum wave function. So there are going to be two wave functions for the same electron. This can be thought to be something like that you can have many projections of the same house. You can have a left projection, right projection, or bottom. There are many, as many sides you take pictures of, but they are all, these two are many, but they are all about the same, eventually electron, but here in this example the same house. But this is just educational mental preparation, otherwise it's not the same thing. Electron is not that simple, because in house you can enter, but an electron you cannot enter. In case of electron, you have to just learn how to use a different wave function, different size, not enter. So there's a difference as well between electron and a house. But there's one analogy, and this may be useful. But anyway, we now go to not analogies but actual. Actual is that an electron can have a ground state, an electron can have an excited state, and because of that, now onward I will not talk about a particle, I will talk about a state. So at every state can have many wave functions. For example, the most famous is that the hydrogen atom, ground state, has this position wave function. That means the chances of finding electron are same at every angle. That's the position dependence. But now its energy dependence is almost same as that in Bohr model, namely that the energy of minus 13.6 electron volt has the maximum chances of being found. So this means that is what I'm saying is a result of what is called energy wave function. Same state you can have momentum wave, angular momentum wave function is more well known. That means angular momentum 0 is the only angular momentum. That means the angular momentum 0 has a maximum, actually in this case 100% chances. So this is a statement about angular momentum wave function. So there can be many wave functions for the same. Don't say electron now, learn the word state. There can be many wave functions for the same state. And similarly about the excited state, there are two excited states. They can have, each excited state can have many wave functions. And then the experimentally relevant topic is that what is the probability that electron jumps from, falls down. Whether you call jump or fall down, they are all changes, and the change, the technical word is transition. So if we are suggesting that all wave functions related to a state, and the next slide we have a mathematical way of writing the state. It's called state vector. The immediate application of that would be the state vectors. I mean, I tell you, maybe the dot product of state vector, dot product of ground state wave vector and excited state vector will tell you what is the transition probability of electron going from excited state vector to ground state vector. Now there are two I have talked about position and momentum. Suppose there are 8 measurable quantities. You can have position measurable, momentum measurable, angular momentum measurable, energy measurable. They can suppose there are 8 quantities, and you have to say transition from first to second, first to third, first to fourth, and then sorry, this is not energy. This means this is not that transition I was talking about in the last, not excited state to ground state. It's just a mathematical. Position wave function can be related to momentum wave function. Position wave function can be related to energy wave function. Position wave function can be related to angular momentum wave function, and that is more relevant rather than the state transition. It's wave function relation. So the 8 wave function. How many relations you have? First related to 7, second, first you have counted, the second related to remaining 6, the third is related to remaining 5, and so on. All in all, they have 28 relations. Now first the logic of the situation, then we come to physics of that. And the logic is that if you can think of something, some mathematics, furthermore we have just target in mind, how to implement that, that's come later. So suppose, for only the logic of the situation, mathematics of the situation, that if you have one thing, you have to think about what the name of that, whatever it is. If there's one thing, and they are all, I mean, don't too much take seriously how much a number. The idea is how many, whatever they are, if they are related to one thing, this is also related to that, this is also related to, through that these things are related to each other. If a position related to that, momentum dependence are related to that, through that position dependence is related to momentum dependence. And in that case, if you have 8 quantities, then you have to describe only 8 connections, not 28. That's just a mathematical idea that one thing may be useful logically. No more on that. And more on that you may be thinking, what is that thing? What is the name of? We have to give to that thing. No, mathematical name is a vector. And you may say, what is a vector? If you have been thinking, the vector is to describe direction, but here you take the other aspect of vectors. Here vector A, that is related to x component, and vector A is related to y component. Take it this way, they are all components. Here in this picture, this is another picture in which rather than AX and AY, I called V1, V2, V3. The idea is whatever the picture you take this way or that way or there, all components related to one thing. And because they are related to one thing, they are related to each other. And if you say, so far if it's abstract, then in case of two-dimensional vector, I can make abstract that concrete formula. Because here, AX is related to A, AY is also related to A, and because of that, AX and AY are related to each other. And the relation is that their ratio is tan theta. Detailed expression doesn't matter. The idea is that you just get encouragement that V1, V2 numbers, if they are related to one thing, then there can be mathematics as well. It's not only just talk. It can be mathematized as well. And this is an example. This should encourage you. Now further is that if the relation is, that can be given in mathematical form. If A is related, vector related to AX and AY, mathematical form is that if you vector, you take dot product of I unit vector, you get AX is the same. The crucial word is same. The same vector is related to, if you take dot product with J, to AY and so on. Now say the same thing in another notation called way of writing vectors, and I have to tell you maybe why I'm calling vector. Furthermore, you just see the comparison between this mathematics and this mathematics, which is written in a different style. The style is called notation, and this notation is called Dirac notation. And why Dirac, who is Dirac, and this that comes later, but for the moment just learn, use it. The same thing is given is a pink color. Now is a different, the letter is psi. It's the same here, but here, just I said, you can multiply with I unit vector, multiply J unit vector. Here you can multiply. You know, the multiplication is a dot. Multiplication is a product. Here is a dot product, and the Dirac name for that dot product is bra-ket. This English word bra-ket, don't speak C. C is silent, you can say. You say bra, and you speak this way, bra-ket. It's a bracket, and the bracket is a dot product. So like here the dot product is a number, here the dot product is, but that's a familiar number in quantum mechanics. That's a position wave function. You take with k, you don't know what's the multiplication, but you know the result. The result is momentum wave function. Okay, I tell you, I am writing it psi k. Previously I have written it 3 slides ago as phi k. Both are the name of the same thing, and the two name of same, like a person you can have a name and a nickname. They are about the same person, but they give different impression. And here I tell you what is the impression. Psi k gives the impression, and that's the correct impression, that both psi x and psi a, but both share the letter psi. So that means both are about the same. That's the letter psi gives impression. And the books which use phi k, they want to point out the other aspect, and that is that when the position wave function psi has one formula, and when you use Fourier transform to get momentum wave function, the formula differs. So in another way could be that letters should differ, but both mean the same thing. Coming back to the main thing, and that is that I think I'm repeating. It's a crucial thing is same. The same thing is related to, and now we have a name for it. The same thing is a vector, and this is not ordinary vector. This is no direction. It's a vector because not because of any direction. It's a vector because through dot product, and dot product, if you are asking why I am using the word vector, the dot product is defined for vectors. So through dot product, the same thing, same is the pink, is related to all possible wave functions. You can say all possible components, and that's the picture repeats it. The same thing, and I have given it name. Shown it. Same thing. The psi vector is related, and relation is this to all possible wave functions. Now, if you have to deal with vectors, then I tell you, there will be different kind of vectors. They are not ordinary vectors with direction eventually. So this means you have to learn new mathematics. Okay, you have to learn new mathematics, but not new mathematics about many things. Because if you have a vector, then in a sense the vector, there are few vectors only, and the remaining are numbers. Now, what I spoken in the last sentence, you may have a difficulty in understanding what I spoke, the last sentence, that may be abstract for you. So if it is too abstract, then think of ordinary vector. V is Vxi plus Vyj, and that thing I have written is in this form: vector V vector, rather than V vector I have ket vector, and rather than I and j I have ket, first ket and second ket, and you can have a third ket as well. So you know what I said, I repeat what I said, and it may have been difficult for you, and that vectors are only few. Actually the thing is, independent vectors are only few. In ordinary vector, independent vectors are only I and j. So, and here you can say first vector, second vector. Independent vectors are only few. The remaining are the generalization of Vx, Vy. Now Vx, Vy are numbers. So here R1, R2, if it is 1, then R1. R1 is the first. If it is second, R2 is the second. They are numbers. So the rest is numbers, you have only few independent. And the technical word is few linearly independent. They are called basis vectors. And here this equation, which says that rest are the only numbers, that means those few vectors you multiply with numbers and you add them, you get any vector. So multiply with number, adding, that is called linear combination. You should learn this phrase. Linear combination, I repeat. And now I repeat it, I change the letters and I tell you, this I don't confuse with I unit vector or j unit vector. I is a number which so far is integer. But think of that. This means this is a number which can take out the integer values. But if it can take integer values, I can replace that with x. That means that contain non-integer values as well. And the same equation in the symbol becomes rather than I, you have a x. This sidelines which are actually ket, and I have not told you why it is ket, but whatever it is, you can see that is the same here, and letter R is replaced with psi, and that's a deliberate. I tell you what is the purpose. So Ri is replaced with psi x, is a number, psi x is also a number. But I said deliberate. The deliberate is that, psi x, the name was chosen deliberately, and that is the psi. Now it's not, so far I was talking about only like the mathematics. But now the word tells you that's the physics of it as well, and physics is quantum mechanics. Psi as a position wave function. Now, I make a statement, dummy variable, which to start with is only a mathematical statement. And that means that if you have integration limits x is minus infinity, plus infinity. Now, mathematician will tell you that you can have any other variable as long as your limits are same. And I make use of that. That argument is called dummy variable. And deliberately, I mean, it's not random number, any letter. I choose k. You know what is k? K is, with h bar, it's a momentum. It's a psi k. Psi k is momentum wave function. And then you can have energy wave function. So, so far we are saying that a wave state vector, and I think now you are learning why I call vector. The same vector can be related to all possible wave function. And now you have seen mathematical form of the relationship. The same is related to first wave function, that the same is related to this, the other, the same is related to other. You see this through picture, same is related to this and that, or through equation, whatever it is, the same is related to all. And this basis and a byproduct of that discussion is that you learn this definition called basis vector. Now, this basis vector, the dot product, you know. If it is the first two, if it is the first is I unit vector and second is j unit vector, you know what is the dot product. But with the x, if it is new to you, the question is what is the new question, and what do you need? And I think answer is that what you need is there only dot products. Like here, dot products, here dot products. Why only dot products suffice? I tell you now in the next slide. But meanwhile, I tell you that what we have done is that before going to the next slide, where you have what I spoke about that, but I tell you a summary of that slide is that you have many wave functions and we have all related them to that. So now related to that, one thing is not position, not momentum, it's a general. It's a general, it means related to anything. And the word general is a crucial in quantum mechanics. Eventually the main concrete use of that is that there's something called general angular momentum, which is related to position angular momentum, which is called orbital angular momentum, and spin angular momentum, and so on. So that's the later for the moment which I see what's the next in this lecture. And that is the following, that if you know vectors, you know states. And state is related to all possible wave function. Now, it's not that, now you can, in a sense, you can replace all possible wave function with state vector. And that this way. If it is a vector, now it's also answering why it is called vector. If this is a vector, the ground state is a vector. And you may still be thinking that why it is called vector. If you are trapped, if you are limited to thinking that vector has only direction, but here it's not direction. I call it vector because I can make their dot products. So it's because of dot products I call vector, not because of direction. And you remember the result of dot product is a number which has, the result has no direction. So direction is not necessarily related to vectors. You learn mathematics which is nothing to do with direction, but it has much to do with the dot product. And the dot product is, the physical use is that the dot product, the name of the dot product is bra, don't speak C, ket, bra-ket. Now the bracket is the dot product, and the dot product is a number, complex number, and its square is the probability of transition, you can say jump or fall, whatever you call, probability of transition, the technical word is transition, a quantum mechanical word, transition from one state, psi state to phi state. That's the transition amplitude, and its square is transition probability. Now, how to calculate dot product? You must learn the name of the dot product. That's a bracket. But still you've been thinking what call it bracket or whatever. It's a dot product. And what is the formula to calculate dot product? You may be thinking, if you are still limited to direction, you may think that the AB cos theta. But AB cos theta means direction, angle between hydrogen atom electron ground state and hydrogen atom electron first excited state. Now what can be the angle between them? And the answer is not. You should, rather than thinking of an angle or rather than being limited to direction, you can think of an alternative ways. And when you think of the alternative day, apparently you may think you have to find many alternatives, but what I said basis 2 slides ago, that in vectors you have only few independent vectors, all the rest are scalars. That thing helps here. You have to find dot products not for every vector, only for basis vector. And if you think if it's too abstract for you, first you learn things for ordinary vectors. Ordinary vectors, they are linear combination. That's a phrase you should learn as well. Linear combination. Linear combination means you take first vector, you multiply with the number, you take the second, you multiply and add. For A, similarly for B. Now you have to, if you have to calculate dot product, you have an alternative to AB cos theta, and the alternative does not need direction. The alternative point out that I've said there at slide 7 as well. Independent vectors are only few, rest are numbers, and if you have to dot product, you have to take only few dot products, and in this case only 4. So if you have to find alternative to AB cos theta, you have to find alternative not for all possible vectors, but only a few, countable few. And I'm repeating here that I'm just saying the same thing. You made some practice of learning this ket. Here you don't have bra, but you know ket can be taken dot product. But furthermore, you learn this word as well. Only ket. This any vector can be written as a linear combination, and start learning. This is also a vector that can be written as a linear combination. It's only 2, so I will written some. If it can be as many as you like, then the symbol is this symbol. And the letters are suggestive. So the colors are suggestive. This is basis vector and this is also basis vector. So if you have to learn dot product, a new kind of dot product which is not limited to direction, you have to learn dot product of only basis vector like I, J. Here dot product first with second, first with third, only that. How to do that? Actually, expression in quantum mechanics for dot products are later, I think after 2 or 3 lectures. But to reach that that maybe 3 lectures from now, you have to have some mathematical practice. And to get that practice, what you will be demanded is, till we reach that calculation after 3 lectures, during this 3 lecture, you will be asked to start your practice, and the practice will be that dot product values will be given through a definition, and you have to just implement that definition. And definition is the following. Definition is called orthonormal basis. The basis is a set of basis vectors. An example of basis vector is I unit vector, J unit vector. In ket-bra notation, I unit vector is the first. The label is 1. J unit the second. The label is 2. Now you should get used to the idea. The label need not be an English letter, I, J, or in American style, you have X, Y, not letter, not X, not American X, Y, Z, not British I, J, K, but it's a number. So don't confuse this I with I unit vector. No, this I is integer. It has a numerical value. Numerical value is 1, 2, but why 1? Why 1, 2? It can be 1, 2, 3, 4, 5, 6, 7, 8 ad infinitum. And dot product is the generalization of ordinary vectors. In ordinary vector, you say I dot I, dot product is the same as 1. There the reason is AB cos theta, but now see, I've written in a different way. The reason is not that, but the result is maintained. Dot product with itself, whatever is the reason, now you see, is 1. Maybe AB cos theta or whatever. It's a definition says the answer is 1. Definition only mentions the result. Definition does not say the reason for the result. If it is the same, it is 1 that is consistent with the ordinary vectors. If it is different, like first with second. Now first with second, if you still want example of one dimension, then I can say, although I would like you to liberate from that, but still if you're limited, then I speak for you. That I and J are different, their dot product is 0. Again, maybe I should not say that, but maybe if you are still thinking, Okay, in case of I and j, the reason is ab cos theta, but now think of only result, not be limited to derivation. The result is if the difference is 0. That's the definition it says. If I and j, now this time are not these I, j, these are integers. If the integers are different, the dot product is 0. In the integer, same dot product is 1. And that is, in short, is called Kronecker delta. Now, in this lectures, I have already used the freedom that I can replace this integer with any real number, x. If so, then the dot product will also be replaced, and the name of replaced dot product is that rather than the delta, we have what is called Dirac delta. And next I introduce what is Dirac delta, if needed. Maybe many of you already know, but if for those of you who don't know, I introduce Dirac delta. But meanwhile, I again repeat, maybe hopefully I don't need it, but if this is still a confusion, then I just again point out that this is not x. This is nothing to do with x direction. Yes, it's just a number. This number can be, any number. If x is any number, then the label can be any. So this is not x. This is nothing to do with x direction. But anyway, next the main thing is what is Dirac delta, and that's it. First, I have to Dirac delta is the continuous generalization of Kronecker delta. Apparently, there's a difference. Kronecker delta has two independent variables, I and j, and Dirac delta is a function of the difference, x minus y. They become 1. But I point out that Kronecker delta is also a function of difference. This does not have two independent variables. You take the difference, that is one independent variable, that is only one independent variable. You can name it n. So you understand the independent. So rather than saying that I and j are different, you replace the way of saying, and this time learn this way of saying is that if their difference is non-zero, that's the way of saying so different, and the answer is 0. And rather than saying that if I and j are same, you say if their difference is 0, output is 1. But now hopefully you are learning that independent variable of delta, here is a Kronecker delta, is 1, not 2. So if there's 1, the difference is 0, the output is 1. And if that one number difference is non-zero, the output is 0. Now, hopefully we are ready for continuous generalization of that. That's called Dirac delta. Here the letter I is replaced with continuous x, j discrete is replaced with I, and I have convinced you hopefully that is a function of only difference. The difference is the number x minus y, and here one thing is doesn't change when you go from discrete to continuous, and that is that if independent input is non-zero, then output is 0. Here as well, Dirac delta, if x minus y difference is non-zero, the output is 0. But if here Kronecker delta, if difference input is 0, then output is 1. Here the Dirac delta also has the same feature. If x minus y difference is 0, the output is non-zero. Is not 1, not necessarily 1, whatever it is, but be ready, it's non-zero. And if you want to know what is the value, then rather than value, I tell you the value is optional and I don't spend time on it. What's the value? Because you don't need its value at x and y difference being 0. What you need is, I tell you what is the you need. You need is how to calculate. And in calculation, continue means in calculation you replace sum with integral. In discrete means what is related to Kronecker delta, you have sum of many areas. And if you have a continuous, the first maybe introduction to continuous in my lectures, if you don't know already, is that this continuous sum is replaced with continuous area, they are replaced with continuous discrete area, sorry. They are replaced with continuous area, and that is integration. So that is, if you want to do calculation, then the continuous means the differences between discrete and continuous means the difference between sum and integral. So if you want to know what is a continuous delta function, then you think of an equation which has indiscrete sum, and the equation is the following: that this Kronecker delta, if you sum, as usual way of writing is the two independent variables. Suppose j is 7. If I has any other value, 1, 2, 3, 4, 5, 6, or 8, 9, 10, all other, the other terms are 0, because indices are different. The difference is non-zero. But when only one term will survive, and that is when I is 7. 7, 7, that is 1. 0, 0, 0, plus 1. The answer is 1. And when you go to continuum, remember, summation becomes integral, and the rest of it, if you have understanding, that is very good. If you have some problem with it, you can just replace, you can even memorize, and that will work for most of the lectures of this whole course. Is you can replace I with x, you can replace j with y, and you can replace sum with integral, and the 1 is 1. Either y is fixed, and if your mind is not picking up that y is fixed, I can replace with the letter x naught. That suggests you it is fixed, but I suggest you better get used to that thing, and you should be able to, even if the letter is not x naught, if it is told that y is fixed, think of that y is fixed. Anyway, this is the integration, and this is a generalization. Generalization in another sense, and that sense is that you can integrate any function, and when you have this word any is generalization. This is not generalization I talked about few slides ago. There few slides ago I said any wave function, and here I am saying any function. You can integrate any function, and what is the answer? To learn that, first learn Kronecker delta. Any function means any sequence f of I. It can be f1, f2, f3, and they can have any values. If it is Kronecker delta, you see, again you can take j is equal to, for example, not necessarily 7, I guess 7 was example, now I can say 3. If it is I is different, 1, 2, f1 will be multiplied with 0, f2 multiplied with 0, f4 will be multiplied with 0, but f3 will be multiplied with 1. So answer is f3, and 3 was j, and the answer is fj. So answer is, the only one term survived, that is fj. And if you are thinking that I and j are same, though I could have said it I, and the answer if you have the question why not I, the answer is that if you have summed over I, the answer cannot be a function of I, and that's why you have to prefer j. And now it's the same letter to letter, f is f, rather than I you have x, and rather than j, and rather than summation you have integration, rather than say it's all the same. This continuum version is called, it becomes an integration formula that can be used for any function, and that should add to your list of previous integration formulas, maybe power rule or trigonometric or integration by parts or whatever it is. So you must, if it is new to you, you must remember or memorize or whatever you call it. When you memorize, when you remember its name. The name is called shifting property. Shifting property is a property, but it is a name of integration formula. The word shift is there because x is finished and is shifted with y, which is fixed. So that was introduction to Dirac delta. Now there is something else as well in this business, and that is that if you have learned bra-ket, then you have learned dot product. And now in ordinary vectors, if you take dot product of vector with itself, that is ab cos theta, that is a square, that's a magnitude square, that's a real positive. Now ket-bra notation, if you take a dot product with itself, that's a real. If it is real, we can say it's also magnitude square. But the question is, it is mathematically the question is real, and the answer is that yes, it is real. And calculation for that to get real, you have to use an axiom, and that is that if you use a ket, you take Hermitian conjugate. It's called Hermitian conjugate. Hermitian conjugate is transpose. In matrices you use that. You transpose and complex conjugate. The Hermitian conjugate of ket is bra. Now that's the axiom. Only that new thing you have to use. The rest can be derived from it. And for example, one thing is, if you take Hermitian conjugate of both sides, then here the ket Hermitian conjugate of Hermitian conjugate. Now Hermitian conjugate is they cancel and you have ket, the ket. And the right side you have what happened is a bra. I took Hermitian conjugate, and it's there. So that means if ket Hermitian conjugate is bra, then bra's Hermitian conjugate is ket. Now if your ket and bra are same, then they interchange, but because same, they remain unchanged. And because this is a number, complex number, so you don't need transpose, you only complex conjugate. And the number whose complex conjugate is same, that means it's a real number. So that is introduction to axiom. That's one use of axiom. Another use of axiom is that that also tells you why I have used the word transpose. What is a transpose? Transpose is used in the word is in matrices. What is the matrix has to do with all this? And the answer is here. You can see matrix is a row matrix and it's a column matrix. Don't bother. I take you to that in detail. So, but meanwhile, I tell you, in these calculations, there's one lesson is that to relate that to transpose or matrices. Another lesson is to tell you a generalization of dot product. That dot product, the bra-ket means the bra is different and ket is different. That means that the order matters. Left is left, right is right. In ordinary vectors, you say A dot B is same as B dot A. You say left or right has no significance. Here, if we have given a significance to left and right, the reason includes that only for the left components get complex conjugation and the right not. So that is the significance of left, right. I've made 2-3 claims together. Sorry if it was too quick for you. And I take now mathematically derive. And if you had any problem, hopefully you will be comfortable when I derive the results. And derivation is the following. This is a new equation, not new equation to you. I've noticed this is called linear combination. Any vector can be written as a linear combination of ket vectors. You take Hermitian conjugate. Now Hermitian conjugate, meanwhile I tell you, Hermitian conjugate is written as dagger. Now dagger is, the shape is dagger. Now you take Hermitian conjugate of both sides, and I told you ket Hermitian conjugate, ket is bra, so this is one bra, and this right ket is also bra, and here is a number. It will have no transpose, its number, it will have only complex conjugate. And that is the same, this equation is nothing new, that's written, I've just dummy letter I've changed, rather than R I have S. But now the very first, the middle and the latter, you combine them, S is SI is the same. But rather than here in bra, I've made one change. And that is that I have dummy variable I have replaced with j, and the need is the following. If you keep I, if you don't change it and you call j as j, then you are saying dot product is the only vector with itself. But here that has first, second, third, fourth, and that has first, second, third, fourth, and you multiply the first with second as well. If you have made I with I, you are avoiding that. Don't avoid that. It can different dot products can be. The way is to use this dummy variable argument And if your domain vertical argument you have used it, you have called I as j, and hopefully the rest is simple. If you call it j, then I dot j, and here is ri, it becomes rj complex conjugate. Now in orthonormal basis, that is Kronecker delta, and the use of Kronecker delta I've already made. The only surviving term will be when this is non-zero, then when I or j is same, and I prefer to write it I because I is more familiar letter, ri star ii. And now I tell you the boy with the transpose, which is actually a term from linear algebra, row and column. The reason is the following: first to first, second to third component. This is familiar through linear algebra when you take this, make this row, and then a column. So you know, bra becomes row and ket becomes column, and the ket column, the sounds are same, so it's easy to remember. And another thing is that direction, the left right matters because only for the left, namely for bra, you have complex conjugation. So that is all consequences, two consequences of that axiom: ket complex conjugate is bra, Hermitian conjugate, sorry, is bra. And now I tell you, a few slides ago I said slide number 7. I said that we have generalized it. Generalized these means there are many wave functions, and that is what I started this lecture with. That initial 7 slides, I said that there are many wave functions we have generalized by one thing, which is general, that's related to any. Now question is, what is the mathematics of that? And the answer was that any is related to, any wave function is related to its state vector. And I've told you how it is that, and I show you in a moment. But before that, I do some more practice in using this Dirac ket-bra notation. For the moment, you just suspend that, what quantum mechanics has said, but just learn the use of ket-bra notation. This result is not new to you. This is an ordinary symbol that means V with I. Actually, if you take that, that is a vector multiplied with unit vector, maybe I unit vector is Vx. First with first component, remember with second component, so on. The result is not new. Derivation is, maybe you may say derivation is not needed, but I am taking some time for it because at least in this way you learn, you have a more practice of ket-bra notation. And the practice is the following. This equation is not new to you. I have spoken this any for I have this pink letter, pink word, pink color. Any is a linear combination of that. You multiply with, multiply is bracket. You multiply with I fixed, and here I is a fixed with multiply with means bra, and I fixed means, and here if I is fixed, suppose I is 3, if I use the letter I here, that means I am restricting this thing to 3 only, but that is not, that can be 1, 2, 3 anywhere. To allow that, I have used the dummy variable argument as usual. So call it j, and hopefully the rest is simple. I take it I inside, that's for orthonormal basis, that's the Kronecker delta, and the use is this third use I am making, and that is ri, and that is I proved that left hand side to be equal to right hand side. Now apparently that was the mathematics, and what is the quantum mechanics of that? For that, apparently you do mathematics, but it is hidden quantum mechanics. As a furthermore, only apparent mathematics. It's only discrete to continuous. I is replaced with x. The hidden agenda is, I mean, there's a reason why I have chosen the letter psi rather than R is replaced with psi. I could have replaced with anything, but a psi is deliberate. But the deliberate means is the quantum mechanics is a hidden agenda. But for 1 minute, keep hidden as hidden. Furthermore, apparently you just learn mathematics and more mathematics. Hopefully nothing new is a usual thing. I is replaced with x. It's a continuous generalization. Summation is with integration, and I with x. Step by step is the same, and this way you should learn. Now onward in this course, if I have to do discrete and continuous calculation, I will do only one of them. So from here you should learn. If I have done discrete, how to do continuous. If I have done continuous, how to do discrete. And hopefully you can say left hand side, I is x, j is y, the step to step everything is same, and answer is same. And now what I said hidden, now I make it hidden is explicit. The letter psi was chosen because the result is psi x is a function. So these set of equations say that in slide 7 I said that if you know many wave functions, and now I said slide 7 as well. If you know wave functions, you can generalize them to wave vector. And if you have made wave vector, how to get that wave function? Answer is that. If you want to get position wave function, take bra-ket with position ket-bra. And if you want to get momentum wave function, take bra-ket dot product with k, and you get psi k, which is momentum wave function, and so on. So now we conclude. So what we have learned in this lecture is that all wave functions, recently I was talking about x wave function and k wave function, all are related to one, and one is the vector, and hopefully you know why it's called vector. And another thing we learned is that any vector can be linear combination of the bases. So vector is a complication, but not that big complication. The complication is only for a few, and the few are basis vectors. That's one thing. And we said the Hermitian conjugate of ket is the bra, and we have made 2 uses of that. And the dot product is the transition amplitude from initial to final. And the last thing is that in an example of dot product is delta. So that's all in this lecture. See you in the next lecture as well.